Okay, so I guess you guys have been shared the link for the GAN website video recordings, right? Yeah? No? Okay, okay. The Google Drive, you mean? Oh, the morning, Mr. Subbareddy, Dr. has. That link is there. What? The Word file. You can see the link now? Huh? Yes? Is it opening? Okay. Working fine? Okay. Yeah. So just in case you miss something from the lectures, you can always have a look at the recordings. Okay? Any case, these files are also provided separately. So even if the video is not capturing this screen very well, you still have the files, these files. Okay? this also we can use if you want. Oh, the pointer. But the pointer will have problem, I think. Is it? No, it's okay. It's okay. I think here. For here. Okay. So we are going by that watch, huh? We'll start at 11 by that watch. Yeah. Yes. Yes. Okay. So all right. So welcome to the third day. Yeah, we can wait. Oh yeah, sure. Okay. All right. Welcome everyone. So yeah. So till now we have seen the concept of qubits, right? Concept of multiple qubits. What is the computational basis, right? What is the concept of superposition, right? What are unitary transformations? What is a measurement? Okay. These are the concepts we have seen. Now today we will start with how we model quantum circuits. Okay, quantum circuits. All right. So let us say in a quantum circuit, like in the classical circuit, we have gates, right? So here we will model quantum gates by this kind of a symbol. Okay, symbol. These wires mean these are qubits. Okay, so incoming qubit, and then transformation takes place, outgoing qubit. So let us say the incoming qubit is this uniform superposition of 0 and 1. 1 over square root 2 ket 0 plus 1 over square root 2 ket 1. By the way, before we proceed with the today's material, any questions you have till now from what we have covered till now? If you have any question, you please can ask anytime. Okay? Hilbert space. It is like vector space, but when we have an inner product defined on a vector space, we call it a Hilbert space, because that starts to give us a notion of distance between vectors. Yes, yes. That's also a representation of qubits. Yes, block sphere. Okay, we will not need to cover it so much for our purposes, but if needed, we can cover later on also. Okay. Now, the thing is, we have Hadamard gate, right? We have seen that Hadamard gate takes. Okay, I will have to correct it. This should be 0. Okay, this should be 0. No, I don't want. Is it allowed to eat inside? Okay. Okay, all right. So this should be ket 0. I'll just correct it and resend the file. Okay. And then we model a measurement, okay, by this symbol. This symbol here, measurement. And then you can see that there is a single line. The single line represents qubits, and the double lines represents classical outcome, classical bits. That's why once we have done the measurement, we get a classical outcome, which we represent by double lines. Okay, example, suppose we have a C0 gate, okay, C0 gate. C0 gate, you can see, as we have said, it is a controlled NOT. Controlled NOT. Therefore, what it means? It is a control on the first wire, not on the second wire. Controlled on the first wire, not on the second wire, which means if you have A and B coming in, A goes as is and B transforms to A parity B. Okay? B transforms to A parity B. So, by the way, whenever we are going to specify the action of a gate, okay, we will only specify it on computational basis states. Okay? And you can see that if I specify the action on computational basis state, it specifies the action on all the states extending by linearity. Okay? We will see what it means, concept of linearity. But the point is, once we extend by linearity and specify the action of a gate on computational basis state, it specifies the action on all states. Okay? All states. So we will see that in a bit. But the point is that we will always specify the action only on computational basis state. Okay? So, parity is, okay, yes, this is parity, I will tell you, and XOR is called as parity. Yes, XOR is the same as parity. Parity also known as XOR. Okay, are you guys familiar with the AND gate, OR gate, NOT gate, XOR gate? Very good. So XOR is the same as parity. So what happens in the C0 gate? It is control on the first wire. So this dot represents the control. This represents NOT, parity. Control NOT. A goes as it is, B goes to A parity B. Agreed? This is the action of the control NOT gate. So that means if the input is 0, 0, the output is what? 0, 0. Because this is 0, 0 parity 0 is 0. If input is 0, 1, output is, this is going to be 0 as it is, and this one will be 0 parity 1. 0 parity 1 is 1. If the input is 1, 0, this will be 1 only. Second wire, 1 parity 0. 1 parity 0 is 1. That's why it becomes 1, 1. So you can see, okay, now if the input is 1, 1, if the input is 1, 1, output becomes, this comes out as 1, this second bit becomes 0, 1 parity 1, that is 0. So you can see that if first wire is 0, nothing is happening to the second wire. If the first wire is 1, the second wire is getting flipped. Agreed? That is why it's called controlled NOT. Any questions? No, ket states. We are writing like this, but this means it is for ket states. You see, here I am writing ket states. Okay? No. You see, always think, when we are specifying the gate action, it's a unitary gate, okay? There is no measurement there. But we are specifying the action on computational basis state, but these are ket states. So all these 4 ket states I have specified what the action is. Okay, 4 ket states where they go. Now simply if you want ask, okay, what happens if I take 1 over square root to this and 1 over square root to this? Where does that go? It will go to 1 over square root to this plus 1 over square root to this. Okay, can you please pass the mic?
So that parity, it can be a tensor product.
This is not a tensor. You see, tensor is a product like that. This is a sum. In the circle, inside the circle there is a sum here. In tensor product, inside the circle there is a product.
But it always is that product, like sum. We always represent it as a sum.
Parity.
Yes, sir.
Parity is always sum. Parity is XOR. XOR means sum. It is actually sum modulo 2, if you see. Sum modulo 2. So, it is sum. It is not tensor product. Yes?
What do the 2 lines represent which are
Can you just check if the mic is working? Yeah, okay, yeah.
Like the 2 lines indicate?
2 lines indicate that once you have done the measurement, the outcome is a classical outcome. Remember?
Sir, the book says it is like uniformly distributed 0 and 1. Like
This?
Yes.
No. Double lines in a circuit means it's a classical value. It's a classical value.
That's it. That's the only meaning.
That's the only meaning. Okay? 0 or 1. That is the outcome. Remember, once we do the measurement of the system, then it collapses to one of the basis states. That basis state we are calling as a classical output. Okay? And whatever the outcome, that is what we are calling, representing by double lines. Okay? Or just explain the C0 gate. Okay. No, C0 gate is like this. C0 gate means, you see, C0, C represents control, NOT represents NOT, flipping the bit. Control NOT, control on the first wire, flip the second wire. If the first wire is 0, don't flip. If the first wire is 1, flip the second wire. That means, look at this, 0, 0, the first wire is 0. So nothing is happening to the second wire, 0, 0, 0, 0, 0, 1, 0, 1. But first wire is 1, the second wire is flipped, 0 goes to 1, 1 goes to 0. Clear? Okay. Any more questions? This simply means we are measuring. It's a symbol representing the fact that we are measuring. It's just a symbol. It's like a, sometimes when they, in if you're measuring a weight, it will be showing one arrow like this, na? 80, 90, like that. So, yes, ma'am. Yes? The second. That is happening. 0 is going to 1. First wire is 1, second will flip. Control on the first bit.
Always.
No. It depends on how we have formed the gate. Suppose I do control here, not here. I can do reverse also. Control here, not here.
Then what it is called, sir? Not control.
No. It is still control not. It is still control not. Just there will be control on the second wire, not on the first wire.
Shifting.
It is like that.
Sometimes you can miss the control point, sir. If any effect on the some target.
Miss the control point.
Miss the control point.
That the gate is not acting properly, you mean? Huh? No. Yes. So many times the gate will not act proper. That is the effect of noise. That is how we model noise on acting on the gate. That will require error correction. But we, in this course, for now, we are just assuming that all gates are acting as we desire them to act. Okay? Ideal gates are there, and we are doing the analysis assuming ideal gates.
First wire if you call as a control gate, control wire. The second wire can you call target?
Yes, you can say. You can say target, yeah. Okay? Okay, good. Now, so I was mentioning to you the concept of linearity, right? What does that mean? Look, linearity means if I have a gate U, remember it is a gate and it's a unitary transformation. So we are representing by U. Then suppose I want to know what is the action of U on this linear combination alpha ket V plus beta ket W. Okay? Then that is the same as, see, this is linear. Remember product distributes over addition, correct? Product distributes over addition. So therefore this becomes, and scalars float easily. So scalars float freely. So alpha times U ket V plus beta times U ket W. Agreed? Yes? Simply by linearity. So we are getting this. So whenever we want to know what the gate will do on this state, we can simply see what the gate is doing on ket V, gate is doing on ket W, and then do the summation. Agreed? That is why I said that we only need to specify the action of the gate on basis states only. Because every other state is a linear combination of basis states. So if I know what happens on B, I know what happens on W, I know what happens on alpha V plus beta W. Agreed? And that is how we represent. For example, here, I want to know what it does on alpha ket 01 plus beta ket 11. It is what? The action of U takes it to alpha U on the ket 01 plus beta U on ket 11. Agreed? That is why I said we will only specify the action on basis states. and every other state will be a linear combination of these basis states. So every other state we will know what it is doing. Example here, as I said, suppose it's a this uniform superposition of 0, 1 and 1, 1, it will go to uniform superposition of U0, 1, U1, 1. Agreed? Any questions? Agreed? Good. Okay, so as I have said before, okay, so this is take another example. Control not. This is another gate called control not or Toffoli gate. Control not or Toffoli gate. What happens? Control not. Two controls. A goes to A, B goes to B, C goes to C parity A and B. That means if both A and B are 1, then C is flipped. If any one of them is 0, C is not flipped. Correct? So it is control not. Toffoli gate. So as I said, this represents parity, this is AND, this is OR. Symbol. AND and OR. Okay? Good. Now, let us go to rules of the. Oh, no. I just gave example of 2. Yes. 101 goes to 101. You see, because A and B is not 1. But here 1 goes to 110 because both A and B are 1. So A and B is 1.
If C was 0,
1. Agreed. C is flipped. C is flipped if and only if A and B are 1. In any other case, C is untouched. And A and B are untouched anyway. Okay? This is Toffoli gate. Control not.
We have C parity A and B, right?
Yes.
C parity A and B.
See, for these different things, we have to see how to use these gates to get that. See, actually, if you see later, we will see that how Toffoli gate along with the NOT gate is universal for classical computing. That is, if you have Toffoli gate and NOT gate, you can get AND gate and OR gate also. Okay? So therefore, you can form any circuit. So Toffoli gates form universal set of gates. So this, we can consider other classes of gates also, but we are for now just giving examples of sub gates that we will be using in our circuits. Okay, good. So this is another gate, control not. Rules for the circuit: time goes from left to right. Okay. When we start the circuit, it will start from left, then we'll perform some gate, then we'll perform some gate. Time goes from left to right. Horizontal lines represent qubits. Horizontal line represent qubits. Gates and measurements are represented by various symbols. We just now saw, right? Hadamard gate is represented by some symbol. C0 gate is represented by some symbol, like that. Measurement also represented by symbol. Classical bits are represented by double lines. Classical bits are represented by double lines. Agreed? Okay. Okay, now we are going to look into this concept of partial measurements. Okay, partial measurements. So suppose I have a 2 qubit system and I measure the first qubit only. Okay? I have a 2 qubit system, I measure the first qubit only. What happens then? Okay? That is what we will see. That is called partial measurement. I can measure both the qubits also. I can measure just the first qubit also. I can measure just the second qubit also. Okay? So let us see what happens if we are going to measure only the first qubit. So let us say we have a state psi, which is like this: half 0 0 minus I over 2 1 0 1 over square root 2 1 1. Then what we can do is we can rewrite this state in the following form. Let's take the 0 out. Then we have half ket 0, ket 1 out, minus I over 2 ket 1 plus 1 over square root 2 ket 1. We can just like that rearrange. Agreed? Once we have rearranged, we can write psi as ket 0 tensor some psi 0 plus ket 1 tensor some psi 1. Note that at this point psi 0 and psi 1 do not necessarily have L2 norm 1. Psi has L2 norm 1, okay, but psi 0 and psi 1 need not have L2 norm 1 once we rearrange like this. Okay. Then measuring the first qubit. If we measure the first qubit, the probability of getting outcome 0 is the L2 norm square of psi 0. Agreed? L2 norm square, yes.
When we are measuring this first qubit,
Yes.
its output could be a probability.
No, output is not a probability. Output is either 0 or 1.
0 or 1.
But it is, we are asking what is the probability that the outcome is 0. We are asking, we look at the qubit, right? It is either 0 or 1. But what is the probability? It is 0. What is the probability? It is 1. That is what we are asking. So the probability that the outcome is 0 is given by the L2 norm square of psi 0. Which in this case is what? What is psi 0? Half ket 0, correct? What is the L2 norm square of this? What is the L2 norm square of? Okay. What is the L2 norm square of ket 0? 1. So what is L2 norm square of this? L2 norm square. Half becomes square. So 1/4. Then the L2 norm of ket 0. That is 1. Agreed? We are looking. Probability is only when we are looking. If we are not looking, no probability. Then it is simply the superposition. Okay. Similarly, probability of outcome 1 is L2 norm square of psi 1. What is that? In this case, it is the L2 norm square of this one, this vector here. Agreed? Now, yesterday we saw, right? If we want to find the L2 norm square of this such a vector, what do we do? Summation x alpha x ket x square, summation x alpha x ket x, we want L2 norm square. What is the value? Exactly. Summation x mod alpha x square. Agree? So here mod I over 2 square, that is 1/4. Half 1 over square root 2 square, half plus 1/4 is 3/4. Agreed? In any case, you can see if the probability of outcome 0 is 1/4, the probability of outcome 1 has to be 3/4. They have to form probability, right? So this is how we see the probability of outcome. Any questions about this?
For 0 only we are taking 1 by 4.
0.
There down, probability of 0 is 1 by 4 we are telling.
Yes.
And probability of 1 is 3 by 4.
Yes.
So basically probability of 0, it can be 3 by 4 also, no sir?
Why it can be 3 by 4? Probability of 0, why it can be 3 by 4?
Then why 0 is 1 by 4 sir?
No, because the probability of 0 is the norm square of this vector. L2 norm square of psi 0.
So always it will be like 1 by 4, 3 by 4. Like
No. Not always. Psi 0 sometimes can be different. Psi 1 can be different. Depending on what psi 0 is, psi 1 is, it will turn out to be like. Not always 1 by 4, 3 by 4. Right? It is the norm square of psi 0. But norm square of psi 0 sometimes can be 0.9, 0.8, 0.6, 0.1, 1, 0, whatever. Accordingly it will come. Agreed? For different states it will be different. Okay? So now we have seen if we have a 2 qubit state and if we measure the first qubit, how to find what are the probabilities of different outcomes. Agreed? We have seen how to do that. Now the question is, if I get outcome 0 on the first qubit, what is the state left on the second qubit? Because we have not measured the state on the second qubit. So some state is left. What is that state left? Okay, it will simply be if we get outcome 0 on the first qubit, the state on the second qubit would be psi 0. Remember psi 0 was here. Psi 0, but it will be normalized. Because remember, you have got outcome 0 on the first qubit. Then the state on the second qubit must be a valid quantum state. Should be a valid quantum state. Any valid quantum state must have norm 1. So all we have to do is take psi 0, normalize by its norm. Once we divide by its norm, we will get a norm 1 state. Agreed? I take a state, maybe it doesn't have norm 1. I divide by its norm. I get a state which is norm 1. Agreed? So half ket 0 divided by its norm, right, is ket 0. So basically the state on the second qubit, if we obtain 0 on the first qubit, is ket 0 in this case. The state on the second qubit, if we get outcome 1 on the first qubit, is this state psi 1, remember we had the state psi 1, this one here, divided by its norm. What was its norm? We calculated norm square was 3 over 4, remember? So norm is square root of that. Norm square was 3 over 4, so norm is square root of that, which is square root 3 over 2. Agreed? You divide by that. Whatever it comes out, this is your resulting state. Agreed? Yes or no? Yes? Any questions? Yes?
So does that mean that the second qubit is not 0 or 1, but it is some linear combination of 0 and 1?
Yes,
So it is in superposition.
it is in superposition.
But the first bit we have read, it is not in superposition.
Yes,
Because we have read it.
yes.
And we have calculated, like when we read the first qubit, what is the state of the second qubit?
Exactly. Exactly. Okay? Any more questions? Any more questions? Yes, that's why it's called partial measurement, because we are only measuring part of the qubits, not all the qubits. We measured the first qubit, we got the outcome 1, you mean? Second qubit, you mean? Huh? Yeah, we can measure the second qubit. But accordingly, we'll have to do. What we'll have to do? For example, actually, exactly this is what we are considering here. Here. Suppose we have this 3 qubit state. And I'm not measuring the first qubit, I'm measuring the third qubit. What we have to do then? We have to rewrite this linear combination as this linear combination. That is, take ket0 out in the third qubit and rewrite like this. Then take ket1 out in the third qubit. You see, ket0 if you take out in the third qubit, you get 0, 0, 1, 0, correct? 1 you take it out, you get 1, 0, 1, 1 with these coefficients. Oh, I think I should remove this half from here. Okay, remove this half. Yes, yes, yes. I will just, yeah, no, that's okay. I just mark it. For later I will edit this one. Okay. Okay. Yes, tell me. Ket1. If you bring the ket1 outside, you have minus half ket11 here.
No, I just want to know, like, it's ket111. It's ket111. So we are taking ket11 and bringing ket1 out of the bracket.
Yes.
I am missing that point. How that
Okay,
is valid.
it is something like this. Okay, I have alpha 0, 0 plus beta 1, 0. I am writing it as alpha 0 plus beta 1, 0. Okay? Okay. Just remember, this is 0 here, a 0 here. We take it out. Now, how can we take it out? Okay, let us see. Oh, black pen, black pen. See, what is alpha 0, 0? Okay, let's do it this way. 1, 0. What is this actually? It's alpha 0 tensor 0. Agreed? Because this is just the shorthand for this. Beta 1 tensor 0. Agreed? Yes? Remember the property for distributive property of tensor over addition. A plus B tensor C is the same as A tensor C plus B tensor C. Distributive property of tensor over addition, same as distributive property of multiplication over addition. And this distributive property acts both from the right and the left. I can distribute C from the right, I can also distribute C from the left. Okay. So now I have 0 and 0. This is like my C. This is A, this is B. So what do I do? Alpha 0 plus beta 1 tensor 0. Agreed? Now once we have tensor, remember shorthand, we were just getting rid of it. Shorthand. Because once we have, this is a column vector, this is a column vector. If I write a column vector after a column vector, it has to be tensor. Correct? Remember what we did? 0, 0 is shorthand for 0 appended with 0. Is shorthand for 0 tensor 0. So that's the shorthand we are using. Agreed? Yes.
For the 2-qubit state, if we have a C0 gate acting on the between the 2 qubits, will there be any change to the coefficients alpha beta of the second qubit after doing a partial measurement on the first qubit?
Sorry, what are you saying?
So there is a C0 gate acting between the first qubit and the second qubit.
Correct.
And we are partially measuring the first qubit.
No. You see, you should do systematically. You start with a state, then you are doing a C0.
Yeah.
First calculate the state that you will get after C0. Don't do two things together. First calculate the state you will get after doing the C0. Then you do partial measurement. Don't do together. Okay? Actually, there are two mics. There are two mics. Second mic is here. Okay. Yeah.
Sir, does this only work for independent qubits?
What does only work?
If they are not entangled?
No, here it is entangled, no. What is this? This is all entangled. Correct? Yes. First qubit, second qubit, third qubit, anything you can measure. Just you have to be careful of how you rearrange. You can measure, in the 3 qubit system, you can measure maybe let's say first and the third qubit. Then you will also get an outcome for the first and the third qubit, and conditioned on the outcome you will get some state for the second qubit. That is also possible. You can measure any subset of qubits. Okay. You can measure all the qubits also. If I measure all the qubits, all the 3 qubits, what is the probability of outcome 0, 0, 0? Huh? 1 by 4. What is the probability of outcome 1, 1, 0? Huh? 1 by 4. 1, 0, 1? 1, 1, 1? Probability of 1, 1, 0? Huh? Because it is not here. Its coefficient is 0. Agreed? So that covers what we wanted to cover here. Now let's go to, okay, now we can see our first algorithm, Deutsch's algorithm. Deutsch's algorithm. Okay, so what is the problem here? The problem here is, suppose we have 2 bits in the database, 2 bits in the database, okay? And I want to know what is the parity of the 2 bits. I don't want to know the 2 bits, I only want to know what is the parity of the 2 bits. Okay? So as I say, XOR. XOR. If it is 0, 0, XOR is 0. If it is 1, 1, it is XOR is 0. If it is 0, 1, XOR is 1. If it is 1, 0, XOR is 1. So I simply want to know what is the parity, what is the XOR. If I have to do this using classical queries to the database, how many queries I will need? How many queries I will need? I have 2 bits on the database. I want to know what is their XOR. What will I have to do? Can I do with just reading the first bit? Can I do just reading the second bit? I have to read both the bits. Without reading both the bits, I cannot know what is the XOR. Now in the quantum case, we will see how we can do with just 1 query to the database. So this is one of the simplest problem with one of the simplest advantages. 2 queries versus 1 query. 2 classical queries versus 1 quantum query. However, that quantum query will be a query in superposition. We will do a query in superposition to the database. Okay? Okay. So the way we will model queries to the database is by this so-called black box model, black box queries. That is, there will be 2 locations, A, 2 locations, because there are 2 bits in the database, right? Location number 0, location number 1. If we send A equal to 0, output will be the bit written in the database, location number 0. Correct? That is how we will model our queries. If we put A equal to 1, then the black box will return to us the bit written in the database, bit number 2, which is location number 1. Just there are 2 bits, but we are calling location 0 and 1. Agreed? So A is the location of the 3, 0 or 1. F of A is the bit written on that location. F of A is the bit written on location A. Agreed? That is how we are modeling our query. This is our query. It is modeled by this function F from 0, 1 to 0, 1. Agreed? Input is also 1 bit, output is also 1 bit. You see this? Okay. However, there is one issue. Okay? Right? So, so you can see we have this function f, input could be 0, 1. Now we are saying there are 4 different possibilities of the function depending on the output value of the function, correct? The output value could be 0, 0, could be 0, 1, could be 1, 0, could be 1, 1. These are the 2 bits written in the database. The 2 bits written in the database, this is the bit written on the location 1, this is the bit written on the location 2, or location 0, location 1. The bit could be 0, 0, it could be 0, 1, it could be 1, 0, it could be 1, 1. 4 different possibilities. Agreed? Determine if f is a constant function, that is f0 or f3. If you see f0 or f3, the parity is what? Parity is what? 0. XOR is what? XOR of 0, 0 is what? XOR of 1, 1 is what? Here what is the XOR? Here. So we are determining if it's a constant function. Constant function is where both the values are the same, 0, 0, 1, 1. Or it's a balanced function, that is 1 is 0, 1 is 1, 1 is 1, 1 is 0. Agreed? So we are simply trying to determine whether given f is actually this is another way of saying the same thing, whether it's a constant function or it's a balanced function. That's all it is. And we are saying we are allowed black box queries to f. This is the black box query. As we have seen, 2 classical queries are necessary and sufficient, correct? 2 classical queries are necessary, they are also sufficient. 1 quantum query in superposition is necessary and sufficient. We cannot do with 0 queries. Agree? 1 query will be needed, but that is sufficient. Alternate way of framing the task, which I mentioned before, there are 2 inputs in the database, 2 bits, 0, A0 and A1. In the database, which can be queried, determine the parity of the 2 bits, A0, A1. That is the alternate way of phrasing the same task, which I had mentioned before. Agreed? Any questions on what the task is? Is the task clear? Clear? No. Okay. Then, here is the mic.
So can you just repeat it? I still didn't get it actually.
Okay.
So maybe I'll try.
Yeah. Task is the following. We have 2 bits in the database, A0 and A1. 2 bits. A0 can take 2 possible values, 0 or 1. A1 can take 2 possible values, 0 or 1. It is written in the database. We need to query the database to find the value of A0, find the value of A1 and all that. Our task is to determine what is the XOR of A0 and A1. You know what is the XOR function? That's all is our task. F. Okay. How is related to F? The way it's related to F is the following. Okay, let us first look at this concept of black box queries. Okay. Concept of black box queries. There is a black box, so there is a function f, okay? There is a function f, which takes input is 1 bit, output is 1 bit, okay? Function f, input is 1 bit, output is 1 bit. You want to query f. You can, one possibility is input comes as a, output comes as f of a. Agreed? You don't know what is f actually. You can find out what is f by querying it at different inputs. You can query it at 0, you can query it at 1 and all of that. Agreed? So, but this transformation A to f of A is not a invertible transformation. Because suppose I give you a function which at 0 also takes value 0, at 1 also takes value 0. It is a possibility. Agreed? Yes? In which case this map is not a one-to-one map. Therefore, it is not invertible. Therefore, it cannot be unitary, because unitary has to be invertible. Agreed? So, the way we model queries to F is via a different thing called BF. BF. Black box query to F, BF. How do we model it? Input is A and B. For this function, which A will come out as it is and B will be B parity f of A. Okay? Remember, f of A is also 1 bit, B is also 1 bit, A is also 1 bit. Okay? So, if you take the possibilities for A and B, 0, 0, 0, 1, 1, 0, 1, 1, 4 possibilities for A and B. Agreed?
So here A and B are the two combinations of inputs which we are.
No. We'll get to that. Here simply we are saying A and B, which are the two inputs to BF. There are 4 possibilities: 0, 0, 0, 1, 1, 0, 1, 1. What is the output? A comes out as it is. So 0, 0, 0, 1, 1. This is as it is. Here what is happening? B parity f of A. So if B is 0, what comes out is f of 0. If B is 1, what comes out is f of 0 parity 1. What is f of 0 parity 1? F of 0 flipped. Correct? So it is, bar means it is flipped. F of 0 flipped. If input is, here is 1, here you get f of 1 parity 0. So that is f of 1 itself. Here you get f of 1 parity 1. So f of 1 is flipped. You see this? The action of this box is given by this table here. More compactly, it is given by like this. A goes to A, B goes to B parity f of A. Now we can see one thing. Even if f is 2 to 1 function, okay, doesn't matter, f is not 1 to 1, but BF is 1 to 1. BF is now 1 to 1. It doesn't matter what f is. Okay. Why is BF 1 to 1? You see this. Suppose I have 2 strings A and B, 2 possibilities, right? I have to show that for any of the 2 possibilities here, among the 4 possibilities, the output should be different. If I show that for any 2 possibilities the output is different, that means it is a 1 to 1 function. Agreed? Yes or no? Fine. Let us say if I take 2 strings here, 0, 0, 1, 0. Because in the first bit it is different, 0 and 1, it will remain different here because A goes as it is. So if the first bit is different, output is different, not a problem. Agreed? Yes? Now let us say the first bit is the same. If the first bit is the same, the second bit has to be different because these are different strings. Second bit is different. But second is different, what is coming out? F of 0 flipped. Correct? If B is different, this output will be different. One time f of A, one time f of A flipped. So therefore, in all of the 4 cases, you take any 2 cases, output will be different. Even if suppose I have a f such that f of 0 is 0, f of 1 is also 0. in which case this is not invertible, but this remains invertible. Agreed? So therefore, we will always implement our f in this form with the bf there. With the bf there. Okay? Okay, now your question, what is this?
What I understand is A is your query, B is your input which you are going to find out what will be the output, right? Is it correct?
Yes, A will specify the location,
Yeah. And B
whether
will
the first bit or the second bit.
B is the user defined.
And f of A is the value written in that location.
F of A is a value. Like,
See, there are two locations, okay?
okay, there are two locations. First location gives you the.
If A is 0, I am looking at this location. But the value here can be 0 or 1. So A will be 0, meaning I am looking at this location. The value written there is f of A, f of 0.
Okay, A is the position and F of A is the value.
Is the value written in position A. Got it?
Yeah.
That's how we model it. Any questions? Any questions?
And what about B?
B is just used to do this parity.
So B is given by the user, right?
It will be, we will provide the B.
So there are
Depending in our algorithm, we will provide.
So there are like one query on A and B is like our constant which we are given.
Correct.
Okay.
B is we will use the wire where, that is the wire where the output will come.
Okay.
But it will be parity with B. The reason we are having this B is to make the entire operation of query invertible, independent of what f is.
Still you count the number of queries to be one only, right?
One only.
Okay.
Because look, this is, you can put a superposition of the inputs here. But the number of time you are invoking BF is the number of time we are querying F. Number of time we are invoking BF. I could be invoking BF on some superposition query also, but that I will count as only one. That's the point of quantum queries. Quantum queries can be in superposition. But the number of times we will invoke the BF gate will be the number of queries we are doing to the database. That is how we will count. Agreed? Even classical also, if you are querying, number of times you will invoke the F gate is the number of times you are querying. Agreed? Any questions?
Our task was to find out the XOR between two inputs, right?
Yes.
So this is the procedure you are telling?
No. We have not seen the procedure. I was just telling how to model queries to the database using this unitary BF. That's all. How to model the queries. We have not yet seen the procedure. The actual circuit we will see. Okay? Okay. So here is the circuit, and then we will go through slowly the analysis. By the way, before, so Professor Subbareddy will be taking tomorrow morning one class, right? 9:30 to 10:30 or 9? 9:30 to 10:30 he will be taking one class tomorrow morning. That he will cover the asymptotic notation, okay? And 11 o'clock we, as usual, we will have our class, okay? Tomorrow. Now tomorrow afternoon there is a possibility because Friday morning we are going to have a Qiskit class. That will be online, okay? So for that you please bring, all of you bring your laptops, because you can only do that online only. You please bring your laptops. And if there is some configuration to be done, etc., etc., we will send one email to you tomorrow, so that Friday morning you are ready with your laptop. Even otherwise also it is, I think, not very difficult. Morning also when the class starts, first 10 minutes or something, you can do the configurations. Okay. So tomorrow, Friday morning 11 to 1 we will do the Qiskit class. That will be online. So Thursday afternoon there is a possibility that we do a 2-hour lecture again, not the tutorial, because we need to cover whatever we need to cover theory for the Qiskit class. So depending on what we are able to cover today and tomorrow morning, tomorrow afternoon is a possibility we do additional 3 to 5 one class lecture, not tutorial. Today we will have still 3 to 4 tutorial. Tomorrow we may have 3 to 5 lecture, okay, depending on what we are able to cover, etc. So tomorrow morning Professor Subba Reddy will be covering also one more class, 1 hour, 9:30. So please be here 9:30. So tomorrow we may have a 5-hour marathon. Okay, it's a possibility. Why we are saying BF is invertible? Okay, that is because, you see, there are 2 bit of input to the BF, 2 bit of output to BF. If I tell you that for every 2 distinct inputs, the outputs are distinct, that becomes invertible. You see, if a function from 2 bits to 2 bits is a 1-to-1 function, then it's invertible, correct? Because it is a onto function also, right? 2 bits to 2 bits, 4 possibilities to 4 possibilities. If for every 2 distinct possibility the output is distinct, then it is invertible. Agree? Yes. You see, if the 2 bits have a value different, then the output is definitely different, because A goes out as A. Now, if A is the same, then B has to be different. Because B is different, f of A is kept as it is in one case and flipped in the other case. Therefore, it has to be also different. You can see it. Just the 4 possibilities, you just stare at it for a while, you will see that all the 4 possibilities are different. Okay? All right. So, let us look at the circuit for Deutsch's algorithm. Circuit is as follows. The input we keep as ket0 on the first wire, ket1 on the second wire. Both of these are Hadamard transformations. Hadamard is HH. Okay? Followed by BF. BF we have already seen what is BF. Followed by Hadamard on the first wire. Second wire we forget. We throw it to the trash bin. This means trash. First wire we do Hadamard followed by measurement. Whatever is the outcome, that is our outcome. Okay? Circuit is clear. You can see now, we are using only one invocation of BF. Therefore, it is only one query to the database. However, that query will be in superposition. We will see. The query will be in superposition. These things you can see, right? Okay, we will go through it one by one slowly, okay? Any line you don't understand, you please ask. It's important for us to, because this is the first analysis we are looking. So it's important for us to go slowly and understand the analysis. Okay. What is it? Look at the state at this point. This is 0, this is 1, H. The state at this point is what? H done on 0, tensor H done on 1. Agreed? Yes? This state is what? 0 tensor 1. H done. By our formula, it is H tensor H ket 0 tensor H ket 1. Agreed? Any questions? Good. What is H ket 0? 0 plus 1 over square root 2. Remember that? 0 was, ket 0 was going to uniform superposition of 0 and 1. Ket 1 was going to 1 over square root 2 ket 0 minus 1 over square root 2 ket 1. Agreed? Remember the Hadamard transformation of 1 over square root 2, 1 over square root 2, 1 over square root 2 minus 1 over square root 2. The minus is very important. So 1 goes to 0 minus 1. Agreed? Good. Under 2, 1 over square root 2, 1 over 2, I just take it out, common half. Now we just write this tensor, we open it up, okay? 0, 0, 0, 1 minus, right? 0, 1 minus, 1, 0, 1, 1 minus. Agreed? Remember the minus here. So this minus becomes 0, 1 with minus, 1, 1 with a minus. It's very important to track this minus very carefully. You make 1 minus plus, it is a problem. Okay? Good. Now we apply BF. BF. What happens? 0 is as it is, 0 goes to f of 0. 0 is as it is, 1 goes to 1 parity f of 0. Remember, B goes to B parity f of A. So 1 goes to 1 parity f of 0. What is 0, 1? 0, 1, what happens? The action on 0, 1, BF. 0 goes as it is. 1 goes to 1 parity f of 0. You remember? A, B. A goes out as it is. B becomes B parity f of A. So if it is 0 and 1, 0 will come out as it is, 1 will go to 1 parity f of 0. 1 parity f of 0. That is what happened here. 1 became 1 parity f of 0. Any question? Is this confusing? Is this confusing? You see, for all the different terms in the superposition, we are separately applying our unitary transformation. Concept of linearity. Correct? We said we will specify the action of the gate on each basis state and extend it by linearity. That's precisely what we are doing here. For each of these things, we are simply applying it by linearity. So why does 1, 0 go to? 1 goes to 1. This is the first wire. Always think the first wire. First wire untouched. 1 goes to 1, 0 goes to 0 parity f of 1. So that is f of 1. Where does 1, 1 go to? 1 goes to 1, 1 goes to 1 parity f of 1. Agreed? Zero, 0. 0 goes to as it is, 0 goes to 0 parity f of 0. 0 parity f of 0 is the same as f of 0. That's why we don't write it. 0 parity f of 0 is f of 0. Agreed? Agreed? Any question? This is the first time we are seeing this thing, so we can go slow. You stare at it, okay? Looking okay? Okay. That is the action of BF. Now what we are going to do? We are going to do some algebraic manipulations. some algebraic manipulations. What do we do? So remember there is a 0 here and a 0 here, right? So we take the 0 out. Put bracket f of 0 minus 1 parity f of 0. Just put it in the bracket like that one we did. Okay? Take 0 out. Take 1 out here. F of 1 minus 1 parity f of 1. Simply that algebraic manipulation. Now what is happening? Now we are going to use some formula, okay? We are going to use some formula. First thing, look at this formula here. What is it telling us? For any value of a, ket a minus 1 parity a is minus 1 to the a, ket 0 minus ket 1. Okay. Let us look at this formula slowly. Suppose we put value of a to 0. We put value of a to 0. What do we get here on the left hand side? Ket 0 minus ket 1. What is on the right hand side? What is minus 1 to the 0? You see? Minus 1 to the 0 is 1. Anything to the 0 is 1. So this one is 1. What is this? Ket 0 minus ket 1. So if a is 0, left hand side is ket 0 minus ket 1, right hand side is ket 0 minus ket 1. Agreed? Any question? Now put a equal to 1. Left hand side is ket 1 minus ket 0. Right? 1 parity 1 is. So ket 1 minus ket 0. That is the left hand side. What is the right hand side? Minus 1 to the 1. What is minus 1 to the 1? Times this one. That is what? Ket 1 minus. The sign will flip. Agreed? So this formula holds for every value of a. Agreed? Okay. So that is the formula we are going to use here. There is f of 0 minus 1 parity f of 0. We use this formula here. So we get minus 1 to the f of 0 out, 0 minus 1. Agreed? Think of f of 0 here as the a here, right? F of 0 minus 1 parity f of 0. Exactly the same thing. We take it out, minus 1 to the f of 0, 0 minus 1. This 0 remains as it is. There is a ket 0 here which remains as it is. This one becomes minus 1 to the f of 0, 0 minus 1. Agreed? Just look at it slowly. Is looking okay? Yes? Very good. Similarly here, this 1 will be as it is. This one will become minus 1 to the f of 1, 0 minus 1. Because it is f of 1 minus 1 parity f of 1. Exactly that formula. Agreed? Okay. Now you can see one thing, we will use another formula here. For a and b, 2 bits, minus 1 to the a times minus 1 to the b is the same as minus 1 to the a parity b. A XOR b. If I do minus 1 to the a times minus 1 to the b is the same as minus 1 to the a parity b. You can see that because if a and b are the same, suppose a and b are both zeros, what is the left hand value? Okay. What is the, if both a and b are 0, what is the left hand value? What is the right hand value? If both a and b are 1, what is the left hand value? What is the right hand value? If a is 0, b is 1, what is the left hand value? Right hand value? If A is 1, B is 0. Okay. So this formula is also correct. Now we are going to use that formula. So we reached here, right? We reached here. Now, okay, one thing we will do first. Remember, this is 0 minus 1 here, also 0 minus 1 here, the second qubit. We take it out. Okay? Common. Now you can see now the first qubit becomes what? This minus 1 to the f of 0 0 plus minus 1 to the f of 1 1. Agreed? Look at what is happening here. This 0 minus 1 comes out as it is. Then what is this left? Minus 1 to the f of 0 0, correct? And here minus 1 to the f of 1 1. That is what is left. Agreed? All this is just algebraic manipulations. Okay? We are left with this. Now we are going to use this formula. Now what we are going to do? We are going to take this minus 1 to the f of 0 out. Okay? But when we have the minus 1 to the f of 0 out, what is left here? Minus 1 to the f of 0 parity f of 1. Agreed? See, if I take minus 1 to the f of 0 out, I can say I can divide by minus 1 to the f of 0, right? But dividing by minus 1 to the f of 0 is the same as multiplying by minus 1 to the f of 0. Okay? It's just the sign. But when I multiply by minus 1 to the f of 0, I use that formula, I put the f of 0 on parity. Here. Agreed? I just take minus 1 f of 0 out. Here, what I have to do, I have to divide by minus f of 0, right? Here there is just minus f of 0, so just get a 0 here. Second one, I should divide by minus f of 0. But minus 1 to the f of 0, if I divide, is the same as multiplying by minus 1 to the f of 0. But when I multiply by minus 1 f to the 0, I use this formula, I get f of 0 parity f of 1. Agreed? Good. Now we are going to ignore this qubit, right? Second qubit is ignored. But now you can see that look at this value here. This value, I zoom it. No, not n. Where is we have the n? This one? This one? Yes, A. Yeah, that one formula we all used before. That formula we used here. This one we used here. Correct. Yes. Okay. So, right. So we had reached here, right? Correct? We had reached here. Now there is one more formula, which is this one. For every value of A, 1 over square root 2 ket 0 plus minus 1 to the A ket 1 goes on Hadamard transformation goes to A. Why? Put value of A to 0. This is ket 0 plus ket 1. Where does it go to? Ket 0, right? Hadamard transformation. Remember, Hadamard transformation takes ket 0 to 1 over square root 2 ket 0 plus ket 1. And Hadamard is its own inverse. So it takes 1 over square root 2 ket 0 plus ket 1 to ket 0. It takes ket 1 to 1 over square root 2 ket 0 minus ket 1. So similarly, it is its own inverse. So it takes 1 over square root 2 ket 0 minus ket 1 to ket 1. So if A is 0, this is ket 0 plus ket 1, it goes to ket 0. If A is 1, this is ket 0 minus ket 1, it goes to ket 1. With the minus sign, it will go to ket 1. Agreed? This is the when you apply the Hardeman transformation. Remember, in the circuit, after we have done the BF, we are applying the Hardeman transformation, okay, on the first wire. So here, once we have reached here, we are applying the Hardeman transformation on the first wire. If we use that formula, what happens? Ket 0 plus minus 1 to the whatever 1 goes to that whatever. F of 0 parity F of 1. Agreed? So we got F of 0 parity F of 1. This we just measure and output. Second wire we ignore. You see? We got in the first wire precisely F of 0 parity F of 1. This is exactly what we wanted. The parity of the 2 bits. Yes?
Sir, it's the last step, sir.
You just tapped.
From last to third step, sir.
This one.
Yes, sir. Minus 1 to F of 0, ket 0 plus minus 1 to F of 1, ket 1. That formula should be sum up to minus 1 F of 0, F of 0 parity F of 1.
Yes, here.
Why the excess term, sir?
Which excess?
Minus 1 F of 0.
This one?
Yes, sir.
No. You see, here is minus 1 to the F of 0, right?
Yes.
I take it out. So I get ket 0 here.
Okay, sir.
Not a problem? Now what about this? It should be minus 1 to the F of 1 divided by minus 1 to the F of 0.
Okay.
If I take something out, I should divide it here, no?
Yes, sir.
So it should be minus 1 to the F of 1 divided by minus 1 to the F of 0.
Okay, sir.
Huh?
Yes, sir.
So minus 1 to the F of 1 divided by minus 1 to the F of 0. But divided by minus 1 to the F of 0 is the same as, let me do it here actually. Okay. So here minus 1 to the F of 0 ket 0 plus minus 1 to the F of 1 ket 1. I take minus 1 to the F of 0 out. This is ket 0. This one is minus 1 to the F of 1 divided by minus 1 to the F of 0 ket 1. Because once I take it inside, this will be here, this will cancel with this. Agreed? But you see, this is the same as this product. This division is the same as the product because it's simply the sign. You divide by the sign or you multiply by the sign is the same thing. Okay? So this division is the same as the product. Agreed? Yes or no? Now once it is the product, we use the formula. The minus 1 to the parity. And this is still there.
Sir, there is the formula, right, sir?
Yes.
Third formula, sir.
Third formula.
Sorry, third, the second one, sir.
Second.
Sir, this formula.
Yeah.
According to that formula, all the minus 1 of f of 0, ket 0 plus minus 1 f of 1, ket 1 should be summed up to minus 1 of f of 0.
This formula.
Yes, sir.
No, we are using this formula only. We are using this formula only. Just you wait 1 minute. Okay. You follow systematically one by one. You don't jump. If you jump, you will get confused. No, that's all. So you follow this one by one. Okay. Here is we are talking this one. Okay. That is what we are trying to manipulate. No. This expression. Minus 1 to the f of 0 ket 0 plus minus 1 to the f of 1 ket 1. That is the expression. I am taking minus 1 to the f of 0 out. Ket 0 is there. No problem. This one is minus 1 to the f of 1 ket 1. I divide by minus 1 to the f of 0. Agreed? Because you multiply here, this will give you the first term, this will give you the second term. No issues. Okay. Now look at this division. Minus 1 to the f of 1 divided by minus 1 to the f of 0 is the same as minus 1 to the f of 1 times minus 1 to the f of 0. You agree to this? Yes or no? Now I am going to use that formula. Minus 1 to the f of 1 times minus 1 to the f of 0 is the same as minus 1 to the f of 0 parity f of 1. Second formula. Now you got the parity. Now this one is as it is. See, all these things, no, you have to go very slowly. In mathematics, if you jump steps, see, you have a derivation like this, 10-step derivation. You jump step in the first step. Your second step is already wrong. Then the entire thing you are doing after that is just a story only. Okay? That one is no longer any mathematics. So any step you have to be very careful. Okay? You have a 10-step derivation, every step should be right. Especially you do mistake in the first few steps, then gone. There is no way it will correct after that. Okay? So, this one is clear now? Okay. So, finally we got the desired output. Agreed? this is our desired output. We simply measure it and output it. Now the thing this is called, you see, after we did all this and we removed the second wire, right? What happened? You see, usually BF initially puts the value of the F in the wire, right? Like f of 0, f of 1 is put here. But later you see, by all this manipulation, we got the value of f of, like with 0 we got minus 1 to the f of 0, with 1 we got minus 1 to the f of 1. So the value of f actually came as part of the sign. Initially the value came in the second wire. Now we did all this manipulation, we got the value as a part of the sign. The second wire is containing nothing, the second wire is fixed, 0 minus 1, which we trash. The value of f got obtained in the first wire as part of sign. Ket 0 has minus 1 to the f of 0, ket 1 has minus 1 to the f of 1. Agreed? That is what is called as, referred to as phase kickback. F was actually obtained on the second wire. We did some manipulations. F got obtained in the first wire, but as a phase. That is what is called as a phase kickback. We will use this phase kickback often. Okay? Any questions? This one, last line. So this is where we are using this third formula here. So third formula we get this value, right? Look here, what is the third formula? Ket 0 plus minus 1 to the A ket 1 on Hadamard transformation goes to ket A. So here we have ket 0 minus 1 to the f of 0 parity f of 1 ket 1. So A here is like this, f of 0 parity f of 1. correct? That one goes to ket A. What is ket A? F of 0 parity F of 1. Here, minus 1 to the F of 0 parity F of 1. It is in power minus 1 to the power. Right? Yeah, minus 1 to the power F of 0 parity F of 1. Then this one just comes here. Okay? This is, you see, minus 1 to the F of 0, 0. Minus 1 to the F of 1, 1.
So that phase which you are talking is just minus 1
to the F of power, yes.
Okay.
Phase.
Our query was 0 and the phase of that minus 1.
Exactly.
The
Exactly.
function of F.
Exactly. The sign now carries the function value. Sign carries the function value.
Okay, and you get the F that. Okay, the other one is carrying the information whether it is equal function or like whatever function you are saying.
Yes. Whether balance function or
Balance function.
constant function. Parity. F of 0 parity F of 1. If it is a balance function, F of 0 parity F of 1 is 1. If it is a constant function, F of 0 parity F of 1 is 0.
So we can extend this to multiple
Exactly. This is what we are going to do in the Deutsch-Jozsa algorithm. Okay? Deutsch-Jozsa algorithm. Here now input was also 1 bit, output also 1 bit. In Deutsch-Jozsa, input will be longer, output will be 1 bit. But we will still ask whether it is a constant function or balance function. So now you see, this was actually, you can say, oh, this is like a toy problem, right? It doesn't look like a real world useful problem. Toy problem, okay, in one database we have big, instead of doing 2 queries, we are able to do with 1 query. Okay. But you can see, at least it is exhibiting to us the power of the quantum advantage, slowly. But you can see this advantage is coming from the concept of superpositions, right? This entire thing is about superpositions. And the play of the sign, the minus 1 is so important. If you don't have the minus 1, all this analysis will not work. So the Hadamard transformation that has minus 1 is so important. Superpositions, concept of superpositions. But you see now, even if we start with an input which is ket 0, ket 1, basis states. Output also after measurement is a basis state. In between we did all the superposition things. In between we did superpositions. Initially, simply basis states. Output also basis states. In between we did a lot of superpositions. And that gave us the advantage. But you can now see there is a certain there is a certain sort of ingenuity required in designing this circuit, right? If I give you the task, okay, tell me the parity of the 2 bits, design me a quantum algorithm using only 1 query. It is not obvious. Okay, what should we do? So David Deutsch, he came up with this circuit. So there is a certain amount of experience with these things required. Novelty, ingenuity, etc. required for designing this algorithm. But that one will come while you are more experienced with it. Okay? And it is also task specific. You cannot say, oh, give me any task, I will do this circuit. No. Correct? Different tasks will involve different circuits. But and also it is not clear that every task will also give you some speed up. Maybe it will give, maybe it will not give. So here it is a very simple 2 versus 1. Later we will see greater advantage. Simon's algorithm we will see even more advantage. Okay. And then we'll proceed towards Grover and Shor, looking at even more advantage in different settings. Any questions? Yes. BF. BF is the one query. Measurement is not a query. Measurement was simply measuring the wire. BF is the query to F. BF is the query to F. Black box query to F, which amounts to querying the database.
So black box query, classical query, and quantum query are all three different types of queries.
No, 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 no. Black box query simply means I have a function F. Okay. I can query that. I cannot see the function or a circuit of the function or anything like that. All I can do is query that function at different inputs. F of 1, F of 2, F of 3, F of 4. Whatever input I want to put, I will put in. I will get the output F of that. That is called as a black box queries to F. That is, you are not, it is a black box. The function is actually a black box. You cannot see inside it. Only thing is you can put some input to it and get some output. That is why it's called black box query to F. But remember, one thing is you just put in A, get output F of A. Right? That is a black box query to F. But that is not a unitary transformation. So the way we do black box query is we input A and B. We get output A and B parity F of A. That is our black box query to F. You can do that black box query part of your classical circuit. You can do that same black box query as part of your quantum circuit. But the number of times you do that black box query will be counted. You try to design any classical circuit for this. You will not be able to design that circuit by using one-time BF. You try whatever. If you only use one-time BF, your circuit will not work. You must use BF 2 times in your circuit, in a classical circuit. In a quantum circuit, we are able to use BF only once. Huh? That's why it is only one query. Classical circuit, you have to use BF 2 times. You cannot avoid. Okay? That is what it is. Superposition, you mean? Superposition, you mean? Multiple means superposition.
Main purpose of black box, what we can conclude, sir? The main use of black box is?
Black box main use is not main use. It is the way we model our queries. See, how will we, if I have to say, I have designed a circuit which is querying F. I have to give some box which gives me the query, right, to F. That is my box BF. If I have to query the database, I have to use some element in the circuit which gives me the query output, right? That is BF.
Like sir, like in classical computing, we measure the time complexity of any algorithm with like how many unit
So
operations.
actually, we are not counting here the time complexity. The time complexity involves all the operations. Here we are only counting what is referred to as query complexity. Okay. Query complexity means how many times I am using BF. Or in other words, how many times I am querying the database. Database is F. How many times I am querying F? That is what I am counting. That is what it is called as query complexity. Time complexity will be, oh, even the other Hadamard gates, this gate, measurement, everything I have to count. That is called as time complexity. Okay?
So here we have seen the example for XOR, right? Knowing XOR of 2 bits.
Yes.
So similarly we can do for other gates like NAND gate, NOR gate, right? So
not necessary. See, as I said, it is not obvious that if you can do for XOR, you can do for something else. Everything will require designing circuit which is tailored to your task. It doesn't mean you can do one task, meaning you can do other task. Correct?
but we are designing the circuit, no sir, we can use any gate, no, like combination of any gates.
No, no, it's not clear. It's not clear. We could do it for parity. Doesn't mean we can do it for NAND. You see?
XOR also we can't.
XOR is parity only.
XOR, sorry, what we call XOR. We have so many gates, no sir. NAND, NOR.
Yeah. It is not clear that you can, if you can do for parity, you can do for AND, you can do for OR, you can do for NAND. No.
Sir, here we have designed a circuit for knowing the XOR of 2 bits, right?
Yes.
So likewise I am telling, like, can I design a circuit where it will do operation for NAND like that I am asking. Why only XOR?
Because we could design a circuit for XOR.
Only one circuit will design. So many, like, will be designing in real time, will be designing so many circuits now, sir.
Yes, so many circuits, yes. For example, we will design a circuit for factoring. Then you will say, oh, if I can design circuit for factoring, why can't I do a circuit for finding if a number is a prime number or not? Why can't I do a circuit for solving the solving the traveling salesman problem? It is not like that. If you can do for one task doesn't mean you can do for many other tasks. The fact that you can do for one task is because there is a circuit for it and there is an analysis for it. It doesn't mean that you can now start to do for many other tasks. You can do for similar tasks. For example, we'll extend it. Deutsch will extend to Deutsch-Schosa. It's a similar task, but it's like a generalization of the task considered by Deutsch's algorithm. Okay? In fact, you can try. If you want to try, you try. Okay, you are saying, oh, suppose I want to know AND of f of 0 and f of 1. You are saying? You try to design a circuit. See if you can design. No. Again, it depends on the specific task. If there are lower bounds known, then it means, yeah, you cannot design. But it might be the case that for certain tasks, nothing is known. Neither lower bound is known, nor upper bound is known. Neither you know the circuit, nor that you know that you cannot design the circuit.
Can we use the same circuit for 3 bits, sir? Multiple bits, it means.
3-bit input or 3-bit output?
3-bit input.
That means the database has 8 entries. Is that what you're saying?
Yes.
The number of locations is 8.
8.
This is exactly what we are going to do in Deutsch-Schosa.
Okay.
We will extend it.
Okay. Sir, when we are using 2 bits, the second bit will move into trash, right? So when we are using 3 bit, so which bit we are moving into trash? Why the second bit only moving to the trash?
We will see exactly what we will do for the 3 bits. Just you have to have some patience.
Yes.
Okay. In fact, you can see this is lecture 4. Lecture 5 we will consider Deutsch-Schosa. In fact, we can see also here the circuit. This is the circuit for Deutsch-Schosa. Okay. But we will analyze this one. But we will not do it today because we are getting very close to the lunch time. So we will finish with Deutsch today only. We will not go to Deutsch-Schosa. Deutsch-Schosa we will go tomorrow morning. Yes. Yes, very good. In fact, in the evening, we will do a tutorial where we will exactly address the same problem of global phase and why global phase doesn't matter. You can see the relative phase certainly matters, right? Because the relative phase is in the between 0 and ket 1. If you have, then that will matter. But if you have a global phase, why that will not matter, we will see in one of the questions. No, no. What he's saying is, suppose we have a sign in front of ket 0, the same sign, and also the same sign in front of ket 1. Then that will not matter, because that sign will come out, and then it doesn't matter what that sign is. You cannot use it in any manner. But if you have a sign between ket 0 and ket 1, that one will matter. That is what he is calling relative phase, and global phase is the thing that is in front of both, and that will not matter. Okay. So I think there were some students, some participants were not there before. We made a couple of announcements. One is that he has sent the link to Google Drive. That one has some files. Along with that, there is a Word file also, which contains the links to the videos that are being uploaded on the Gyan website. Okay. That is one thing. And I think the announcements about the lecture tomorrow. So Professor Subba Reddy will be taking one lecture, 9:30 to 10:30 tomorrow. He will be covering the asymptotic notation. And then 11 to 1 also we will have lecture. And potentially 3 to 5 also we will have lecture tomorrow. Friday morning we will have Qiskit tutorial. Please bring your laptops. Okay. If we have to install anything, we will try to tell you by Thursday evening. Even if you don't tell, anything is okay, because Friday morning, first 10 minutes, 15 minutes, we should be able to install whatever is needed. Okay. We will do a 2-hour tutorial on Qiskit, 2-hour lecture, whatever you want to call it, on Qiskit. Any other questions? Any questions for the today's whatever we did? Yes. Task.
And how are we considering whether it is balanced or unbalanced? Now suppose when I give an input to my machine, then how it is considering it as balanced or unbalanced? How it is?
I will tell you. What is a task? I have 2 bits on the database, A0, A1. I want to know what is the XOR of the 2 bits. You understand what is XOR? That is my task. But in order to do the task, I have to go and look into the database, right? Without looking, I cannot say. So I look, but now I count. If I look 1 time, I count 1. If I look 2 times, I count 2. Now, if I want to design a classical algorithm to find the parity of A0 and A1, 2 bits written in the database, how many times I have to look? Has to be 2 times, right? I cannot just look at A0 and determine the parity, or just look at A1 and determine the parity. I cannot, right? I must look 2 times. In the quantum case, I am looking only 1 time.
Using the black box function?
Using the BF, because I am using BF only once. So I am looking into the database only once, and I am still able to determine what the parity is. That is the point. Okay. So this is to exhibit an advantage, how we can get advantage using quantum algorithms over classical algorithms. Classical algorithm doesn't matter whether you are doing using supercomputer or this or that, doesn't matter. You have to look 2 times. Oh, you cannot say, oh, I have this very fantastic, supercomputing cluster, whatever. Whatever you do, you have to look 2 times. Doesn't matter how fast you are computing this, that. You have to look 2 times. Correct? So this is giving us an advantage, a query complexity advantage. The number of times you have to query the database, you are getting an advantage. Okay? Balanced and unbalanced simply means if both the bits are 0, then it's a constant function, because both the bits are 0. If both the bits are 1, it's a constant function. Okay. because the first bit represents f of 0, second bit represents f of 1. If both the values are 0, it's a constant function because f of 0 is also 0, f of 1 is also 0. If both the bits are 1, it's a constant function because f of 0 is also 1, f of 1 is also 1. If one is 0, other is 1, it's a balanced function because exactly half is 0, exactly half is 1. That is the difference between balanced function and constant function. Okay? Yes? Yes, here.
Sir, what is phase kickback, relative phase and global phase?
Phase is the sign. In our case, it is the sign, like -1 to the f of 0. That is called phase, sign. The value of f is in the sign. That's why we call it as a phase. Sometimes you have other phases also, complex phases are also there. You can have other phases which are like different, roots of unity, for example. So those will be complex phases. But for now, we are only taking the two roots of unity, which is 1 and -1. Okay? And that is where the sign is capturing us the phase. Phase is simply the sign. Now, what is relative phase? Relative phase means, suppose there is a sign in front of ket 0, but a different sign in front of ket 1. Then it's called relative phase. But with the same sign in front of ket 0 and ket 1, it's called as a global phase. Phase kickback you saw. Clear? Yes? Entangle means, suppose I have ket 0 0 plus 1 over square root 2 ket 0 0 plus 1 over 2 ket 1 1, such a state. Such a state I cannot write as a tensor state. Okay? 1 over square root 2 ket 0 0 plus 1 over square root 2 ket 1 1, I cannot write as a this state I cannot write as a tensor of two states. Okay? I cannot write like this. Okay? I cannot write like this. Because I cannot write like this, we are calling it entangled state. If we can write like this, we will call it independent state. Huh? What?
The connectivity between the two different states is the entanglement.
Yeah, it is a certain kind of a connection, correlation between the two. There are two qubits, right? You can see one thing. For example, if you measure the first qubit, okay, this qubit, it will turn out to be 0 with what probability? Huh? 1 by 2. See here. Correct? It will turn out to be 1 with what probability? When this is 0, what is the second qubit? When this is 1, what is the second qubit? So you can see the correlation, right? Maybe this qubit is here. The second qubit is in moon or even in another galaxy, wherever it is. Okay? I can create these entangled pairs. One will be here, 2 photons. One will be here, another will be in another galaxy. But now, if I measure the first one, it turns out to be 0, the other will automatically become 0. If it turns out to be 1, other will automatically become 1. Connection. That connection is the entanglement. They are entangled. Yes, they are entangled. As he's showing, they are entangled. Okay? So that's the thing. Any other questions? Yes? Okay? So today we saw the first example. We see initially we were just doing the groundwork, understanding all the setup, the math needed. Today we saw for the first time an example of an algorithm where we can see an advantage. Okay? Now subsequently we'll see more algorithms for different tasks. We'll see more and more advantage. Okay? Okay, sorry. Yes. Yes. Okay, all right. So, yeah, so welcome. So, now we will do tutorial 2. So, just a few things. Trace of a square matrix M is defined as summation of the diagonal elements of the matrix M and is denoted trace M. Okay, just these are some few facts we are stating here. If a matrix is there M, its trace is just the sum of its diagonal elements. For square matrix M, trace is the just the sum of its diagonal elements. A square matrix U is unitary if and only if it satisfies U dagger equal to I. This one we have already seen before. Inner product also we have seen before. For two matrices also we can define the inner product, which is trace of A dagger B. It is the same actually for vectors. Remember, for vectors what was it? V dagger times U, right? But V dagger times U is a scalar, so its trace is just itself. But if your matrices A and B, if you do A dagger times B, that's a matrix also. Then you take its trace, that is its inner product, okay, for between matrices. Okay. Now, remember that we were trying to verify various properties. That maybe the product of matrices may not commute, A times B may not be equal to B times A. We can try to do that by some example. Okay, so I will give you an example. You just verify the product is not commute. So I need a volunteer for that. Any volunteer? I will give you the example, just you multiply, see that it is not commuting. Okay. Any volunteer? You will get 1 marks. Please. Okay. You write there write little bigger. Matrix A is 0 1 1 0, no 1 0, 2 by 2 matrix. Matrix B is matrix B is 0 minus I. No, this is I, that one is minus I, the other one then 0. Okay. Now just do tensor of A and B. Very good. Very good. Very good. Yes, very good. So A tensor B. Now do B tensor A. So somebody should record for her name. I don't know who is recording. You are recording, right? You please record. Okay. So are they the same? Yeah. Are they the same? No, right? So we can see if you do A tensor B, it need not be the same as B tensor A. Okay? Correct. Now part B. Okay? Part B, we have to prove that the transpose A tensor B transpose is A transpose tensor B transpose. What we will do is simply take A as 2 by 2 matrix. A is equal to yes, you can erase that, or you can do by the side, doesn't matter. A is equal to A11, A12, that one. Sorry. Right? First row, the first index represents the row. So A11, A12, A21, A22, that's okay. Now write B. Now let us do A tensor B and then do the transpose. What you will get? Okay, maybe because this is going to be big, maybe let us do like this. Take B to be, take A to be just row vector, take B to be column vector. Let us do like that and see, okay, because then it will be maybe simpler, it won't be that long. Okay, you can do like that. Okay. Then A tensor B is A tensor B. Do the transpose now. A tensor B transpose. Okay, now let us do A transpose. A transpose. Wait a second, wait a second. Yeah, okay, okay. A transpose, B transpose, okay. Then you do A transpose, tensor B transpose. Okay, is it turning out to be the same? Huh? Okay, very good. So similarly you can verify for A dagger also, right? The other one that it is saying A tensor B dagger is A dagger tensor B dagger, because it will also involve the conjugate, but you can verify similarly. Okay, then there is A tensor B tensor C. Again you take example and verify, maybe like general example like this you take and you verify. Okay, I mean as such the question is asking you to prove it, but then in the proving you have to take a general n by n matrix or something like that and do it. But the point is that doesn't matter for now, we can just take, but here also we are not taking specific numbers, right? We are taking general and we are trying to verify. So we can try to do like that. Okay, similarly part D, which is that the tensor product satisfies these properties. So okay, so these things we can try to just verify by taking the examples. You want to verify some other property, or you're satisfied it can be done? Huh? Can be satisfied, right? Okay, now maybe okay, so thank you very much. Yeah, you raised that one. Okay, so now let's try to do F. Okay, volunteer for F. So actually let's try to do this little bit more general. If U is a unitary matrix and V is a unitary matrix, then U tensor V is a unitary matrix. Let's try to do that one. Two different matrices. U tensor V. Okay. Let's keep it general. Here we keep it general. In fact, we don't even have to write U as U11, U12 and all that, okay? You simply just take U and V and do it. Yes, that is correct. Yes. Yes, you want to show that. Yes, you have to prove that, exactly. No, but this is, you are only taking one example. Because we want to prove more general for any U and V. Example, yes, yes. Is it visible what he is writing? Not visible, right? Just change the pen. I think it's not visible. Is there like a glare of the light? Then you put it in front little bit. Maybe you can turn off that light. No, turn off this light, I think. Oh, I don't know. Still glare, Turn on that light. You can, sorry. Which one, is it okay or no? Sorry, they are saying turn on that light. That one. Is it better? I think this is too far away. Let's bring it here. That's it. Good. See this, so it's okay. You guys can see this? Yeah, can you please take the mic and then explain? Okay.
Video presentation and live streaming, they need lighting, sir. That's why we are placing it back to the light, sir.
Okay. But the problem is if you put the light on, then it is a glare on the screen. Then they cannot see because of the glare. If you want, we can switch on this light. You want to switch on this light? Then you can switch on this light. But see if there is a glare or not. Yeah. Okay, so so he wants to show that U tensor V times U tensor V dagger is identity. Now what happened? We have seen before example that if you do U tensor dagger, it's the same as U dagger tensor V dagger, correct? So he replaced by that one. Now he is multiplying.
But this step I am not sure.
This step you have to remember, you have to use write down the formula. I will tell you the formula.
Yeah. Okay.
Erase that one. A tensor B bracket times C tensor D tensor. Use the pen. This pen is always a problem. Both the pens are, we really need a bunch of good pens because all the pens are not working. Then you have to, is it working? No, then use blue or something. Maybe blue is better, red is better. Better, right? Yeah. Okay, formula is A times C. This formula we have seen like 3 times. A times E tensor B times D. Correct? Yeah. This is a very important formula. We will use it many times. Use this formula. Correct. Yes. Yes. What is identity tensor identity? Identity. Correct? So this is the way we can do it. So this is what shows that if U is unitary, V is unitary, then U tensor V is unitary. Same way we can continue even more. U is unitary, V is unitary, W is unitary, then U tensor, V tensor, W is unitary. Okay? Very good. So that one is done. Now let us go to question 2. This is the question that Professor Subbareddy had asked in the morning. Okay. Two quantum states described by vectors V and W are said to be equivalent up to a global phase if W equal to e to the minus I theta V. Okay. Two quantum states are vectors W, V and W are said to be equivalent up to global phase if W equal to e to the minus I theta times V. E to the minus I theta is a complex number. Okay. Do you know this formula? E to the I theta is cos theta plus I sin theta. Okay. This is a complex number. This is a real number. This is a real number. This is a imaginary number. So this is a complex number. You know this beautiful identity, right? Correct? E is it's a real number. It's not rational. Pi is a irrational number. I is a imaginary number. You combine all this, what you get? Simply a integer even. You do e to the 2 pi I is 1. Right? You combine so many complicated numbers, you get a very simple number. Correct? Anyway, so, but if we are switching on this side, can you guys see this? No. That is another problem. So, but how about like in the camera, is it getting captured or not? Like this, if we do, camera is coming, not a problem? Okay. Okay. I think this is okay. I think this is okay. Correct? Okay. You need the. Oh, you're just saying you didn't understand the question, right? Question is saying this. You see, suppose I have two vectors, two quantum states, V and W, given by W equal to e to the minus I theta V. Suppose. Yes. Okay. For some real number theta. Show that V and W are completely indistinguishable when this is the case. That is, show that performing any unitary on V and measuring gives precisely the same distribution of outcomes as doing so on W. Okay. Now, okay, let us have a volunteer for this. We will do it together. Okay. Let us have a volunteer for this. Anybody, please. Anybody, yes. We will do it together, don't worry. You want to come? But I would encourage, because she has come yesterday, I would encourage others to come. You also want marks, right? I don't want marks. No, 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 no. Okay. Yes, please come. When we will do it, it will become clear to you, your question. You take this, erase that one, you can erase everything. You can draw one line in between. Okay, let us do by, take the special case, let us write V equal to V1, V2, just V1, V2 column vector, okay. This is V. W is e to the, okay, instead of minus I theta, let us do I theta, simpler. I theta times V. So, write it, that is equal to V1, V2, very good, that is all, correct, that is W. Now, suppose I am measuring V, I get 0 with what probability? No, not norm square, V is a mod V1 square, correct. One probability, correct, agreed, agreed. Now, if I measure W, what is the probability of getting 0? What is that? You see this? You do the calculation, you do the calculation step by step. No, you can do left hand side, equal to left, no, there, yes. Very good. Very good. Write A plus IB on the right hand side. A plus IB, write bigger, people cannot see. Darker and bigger, or otherwise use another pen. You can use red pen. Use red pen maybe. Now write what is the mod square of this. What is the mod square? What is the mod square? A square plus B square. Okay, you write, erase that one, write A plus IB mod square is equal to A plus IB bracket times A minus IB. Remember, for a complex number alpha, mod square is alpha times alpha star. We have done mod square, okay. So that is equal to, right, what is equal to? A square plus B square, right? Just write little bigger because they cannot see. Okay, now do here. No, you don't have to do the calculation again. Use the formula. Correct. Yes. Now you use the mic and explain. Use the mic and explain.
So in the case of V, the column.
You move little behind so that people can see your board, and now you explain.
So in the case of V, the column vector V1 and V2, the probability of finding 0 is modulus V1 square, and the probability of finding 1 is modulus V2 square. But in the case of W, there's an extra exponential e raised to I theta along with it. In that case, when we're taking the probability of finding 0 or 1, we'll be including the I theta along with e raised to I theta along with it. But e raised to I theta is cos theta plus I sin theta modulus square, and that is actually just 1. So the probability.
No, explain why it is 1.
Because the modulus of modulus square of e raised to I theta, or modulus of cos theta plus I sin theta becomes cos square theta plus sin square theta, which is trigonometrically given as 1. So the probability again comes down to V1 modulus V1 square and modulus V2 square.
Correct. Is it clear now? Clear? You had a question, right? Is it clear now? So you can see that if the vector V is V1 V2, vector W is e to the I theta times V, then doesn't matter what is the theta. So you can think of e to the I theta as the global phase multiplied on V to get W. But now you can see that if W is equal to e to the I theta times V, then if we are measuring V, we are getting 0 with probability mod V square, V1 square, 1 with probability mod V2 square. If you are measuring W also, we are getting 0 with probability mod V1 square and probability mod V2 square. So we cannot distinguish between V and W if we just go ahead and measure 0 and 1. They are giving 0 and 1 with the same probability. So therefore we cannot distinguish V and W. Okay. Now next we will see, even if we can do, usually because we saw an example, remember, that if we just go ahead and measure, we cannot distinguish. But sometimes we can do an orthogonal unitary on it, and then we measure, then we can distinguish. We saw an example. But here what we will see is, even if after do any unitary, we measure, still we cannot distinguish. You can keep the mic.
When we are measuring V and it is giving the same distribution on W. So how I was thinking was, if we can somehow prove that W equal to e raised to minus I theta V is given to us, and somehow we can say that the two states V and W are entangled, then measuring one will result in the measurement of the other.
V and W are not entangled.
So it has nothing to do with entanglement. This
Nothing to do
question
with-
has nothing to do with entanglement.
This question has nothing to do with entanglement. Okay. Now please continue. So now let us say that we do a unitary U on V. Unitary U on V. Okay, U on V. Let's call this vector as UV. Let's call it V superscript 1. No. Is equal to V superscript 1. Okay. I don't know whether V is equal to, okay, no. Let's call it A, just small a. Okay. Then U times W is what? Is equal to U times, right? U times e to the I theta times V is equal to e to the I theta is a scalar, so it can come out the same as UV. Now let's call it e to the I theta times A. Agreed? Yes or no? Now you can see, even now we are going to measure A. Let us say it is A1 A2. We get with probability mod A1 square mod A2 square, 0 and 1. But by the same argument, because it is e to the I theta times A, same argument as before, we will not be able to, still the probability will be, even if we measure UW, probability will be mod A1 square mod A2 square. The e to the I theta will not matter. So you can see, even after doing any unitary and measurement, still we will get the same probabilities in the two cases. So it will not matter. We cannot distinguish it at all. Even if after doing any unitary and measurement, we cannot distinguish it. So that is why this global, if you have two vectors whose difference is a global phase multiplication, actually, yeah, Professor Buradi, we are doing exactly the same question only, the one you asked about the global phase. So maybe for the benefit of him, can you just repeat the argument for V and W?
So there are two vectors V and W which differ by a phase e raised to I theta, or W is equal to e raised to I theta times the vector V.
So there are two vectors V and W. V is V1 V2, we are just doing example of qubit. W is e to the I theta times V. So that is the global phase. E to the I theta is the global phase. W is e to the I theta times V. So now continue.
So the V vector is expressed as V1 and V2. So the probability of finding 0 in vector V is given by modulus square of V1, and the probability of finding 1 in the same vector is the modulus square V2. And in the case of W, if you check, the probability of finding 0 and 1 is correspondingly becomes modulus square of exponential I theta times V1, and exponential I theta modulus of e. I haven't written that down. Anyway, so modulus square of e raised to I theta and v1. So here we could separate out the e raised to I theta modulus square and v1 modulus square, and e raised to I theta can be written as cos theta plus I sin theta, and the modulus square of this becomes cos square theta plus I sin square theta, which is same as 1. So eventually the probability becomes the same as that of v1 or v.
So basically if we have e to the I theta v w, then even if we are going to measure w, we will get 0 with probability mod v1 square and 1 with probability mod v2 square, which is the same as case of v. So no difference. Now you describe about the case of doing after the unitary transformation. Yes. 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 Mod square. You are asking mod square. Yes. Remember a plus ib mod square. You see the thing on the right hand side. Correct. Which is equal to a square plus b square. Yes. If you have a complex number alpha, you write there complex number alpha mod square is equal to alpha times alpha star. Okay, this is the definition. So if you do a plus ib times a minus ib, because alpha star will be conjugate a minus ib, then you do that will become a square plus b square. So therefore for cos theta plus I sin theta, it is cos square theta plus sin square theta. Yes. Okay, and now you describe about the u.
So when we apply an unitary matrix u to both v and w, suppose after applying the unitary matrix u to v, we get a new vector called a. Similarly, if we apply the same unitary matrix to w, we can write it as u raised to u into u times e raised to I theta times v, or we can rearrange it, since e raised to I theta is a scalar quantity, and eventually we'll get it as e raised to I theta times u v, or uv can be written as the vector a. And we can, by same reasoning, we could say that the probability of finding 0 or 1 in both cases will be same.
Exactly. Correct. See the argument? So even if we do the unitary, we won't see the difference. Therefore we can never see the difference between these two vectors, v and w. W is almost the same as v, but multiplied by e to the I theta. So that is why that global phase doesn't matter. You will never be able to see the difference whenever you do any measurement, or even if you do a unitary followed by measurement, you will not be able to see the difference. Clear? Okay, thank you. Okay, now we go to the next question. What is the question? Right. So if we have a matrix A such that, remember we talked about singular value decomposition of the matrix, correct? Singular value decomposition of the matrix. So if we have a matrix A with a singular value decomposition like this, where the V's are orthonormal left singular vectors. V's are called as orthonormal left singular vectors. W's are called as orthonormal right singular vectors. And these S's are called as the singular values. Now suppose, okay, in fact here They are not talking about they are talking about these S's being complex numbers, but I am just saying if we take them as singular values, they will even turn out to be non-negative reals, because we can sort of absorb the complex phases inside the V's. So let us take, for the simplicity, all these S's are non-negative reals, but they are all ones. Okay. So then we want to show that if all the SIs are ones, then this is a unitary matrix. Okay? We want to show that if all the SIs are ones, then it's a unitary matrix. Okay? Now, okay, so I volunteer for this. Anybody? You can come, but I think you have come before. Anybody else who have not come before? Please. Doesn't matter, we will do it together. Yes, yes. Sorry, can you say again? I think you need the mic.
And we do an SVD, then we break it into 3 matrices, like a product of 3 matrices, U sigma V transpose, where your sigma is the eigenvalues which you calculate. So here,
which matrix are you talking about?
Singular value decomposition.
Yes, singular value decomposition.
So the middle, like here we have SI, VI and WI dagger. So this VI will be how will this VI be calculated? Like again, like this, form the eigenvalues and then take them in descending order and all that? Or it's not relevant to the question? You just have to assume that the product is there and it is valid, and we have to just prove that it is a unitary matrix.
Yes, yes. We just have to assume that A is written in this form, summation I SI VI times WI dagger, such that all the SIs are ones, just one. Okay, let's take the case where all the SIs are ones. Okay? Okay? And we try to prove that it's a unitary matrix. Okay? Usual way, whenever we try to prove a unitary matrix, what we do? We do U times U dagger. Do that. You want to do? You come. Erase that one, you do it. Actually, you have to turn the board little bit like this. No. Ha, more like angle little. Ha, yeah. It's okay. Okay, listen, we are taking the SIs to be ones. So you can just get rid of the SIs. SIs are just ones. Huh? No, you don't even have to write. SI is just 1. Remove SIs everywhere. Okay? If it is 1, we don't have to write it. It is given like that, but we can take, the point is, we can take the case that, if mod square is 1, then it is basically e to the I theta. But that e to the I theta we can absorb in V I, and so we can just say that it is 1. So let's take the case of 1, doesn't matter. Okay, now it is summation Wi Vi dagger. Very good. Very good. Now multiply A times A dagger. What are you getting? No, don't do like this. See, whenever you do like this, you will be making mistakes. We should never skip steps. You skip step, you will make mistake. Write A dagger, then you open the bracket. You see, you are suddenly opening the bracket. Write A in the summation form. Erase what you have written. Erase the sigma. Open the bracket. Open bracket. Open bracket. Just open a bracket. Open a bracket. Now write A there. Summation. Close the bracket. Then open the bracket. Summation. Okay. Another thing. Remember what we discussed yesterday or day before yesterday? Whenever you have two summations, you should not use the same index for the summation. Otherwise it is confusing. Summation is left hand side, summation is over I. Right hand side, do it over J. Okay. So first write like this. Do not suddenly write summation something, then you will make mistake. Always go systematic. A, you write A dagger, you write A dagger. Now you open the bracket. Now you open the bracket. How do you open the bracket? Yeah, do it. You can do it there itself, below. Yes. Just write, don't just write first. What are you doing? Just write systematically, don't have to jump any steps. Very good. Yes. Very good. No. Don't jump the steps. You see, anytime you jump the step, you will make a mistake. So don't jump the step. Okay? What is this? What happens if I is equal to J and what happens if I is different from J? Write the two cases. Why will become 0? What is orthonormal? W and V are not given orthogonal. What is given? V1 to Vn are orthonormal. W1 to Wn are orthonormal. Nobody is saying about V and W. V1 through Vn, that set is orthonormal. W1 to Wn, that set is orthonormal. Between V and W, nobody is saying anything. Now you do it. Huh? Wi, Wj will become what? 1. When? You are taking I equal to j or an I not equal to j? Don't jump the step. You jump the step, again confusion. Which case are you taking? Why it is 0? Correct. So Wi dagger Wj is 0 if I is different from j. That is why I not equal to j will become 0, because remember in the middle there is a Wi dagger Wj. That will become 0. So that goes away. I equal to j, right? Wi, sorry, Vi, right? Wi Wj dagger, that one is 0. Correct? Very good. If I equal to j, what happens? 1. So what happens here? Right here now. No, write it below here itself. What happens now? No. I summation you write, no? Now what happens? No. Why you made big I there? This is 1 or identity? What you wrote there? Okay. So now what you are writing here? Yes. Yes. Why it become 1? See, we have to be very careful. We cannot write 1 I. Where it is I, we have to write I. Where is 1, we have to write 1. Why it becomes I? Summation over what? Yes, you write summation I equal to 1 to n. Okay. Write summation 1 equal to n, 1 to n. Okay. So why is it equal to identity? Yes. Why? Did we do this before? Actually, this is one of the questions I think in the assignment 1. Correct? Correct? Second question. But we didn't do it. But it is the second question, which says exactly this, that if you have an orthonormal set, VI's, then summation I, Vi dagger is identity. So write that identity, but this we have to do, we have not done this, but we can still use it, because suppose we have done it assignment 1, we can use it for assignment 2. So this tells us that now A times A dagger is identity, therefore A is unitary. Agreed? Yes? Yes or no? No, no, summation already we have done the whole summation here. Correct. That goes away. 0. What does not hold true? No. The unitary has a summation already. A unitary has a summation. Unitary doesn't have I and j. Unitary has a summation over. Look, what is the A? Summation over I, Wi times, sorry, Vi times Wi dagger. There is no I and j there. There is a summation there. You see? Correct? You cannot say, oh, I is different from j. In the definition of A, there is no, it's a summation over I. Clear? Any questions? Any questions? Okay, I think we are past time, correct? 3 to 4. No, no, yeah, 3 to 5 is there, but the thing is that one is in the schedule, it is like lecture or whatever, but what we are doing here is a tutorial only. So this one is there. Okay, maybe, I don't know, maybe we can try to okay. So there are other questions also in assignment 2, okay. You please try to do it yourself, okay. See, I think somebody was suggesting that we should also give some homework exercises. So these are whatever we are not discussing, you can take them as homework exercises, okay. Later we will be providing solutions to some questions, okay, but the solutions will only be provided between the participants here. It won't be available online or anything, it will only be provided here, okay. But some of the questions we are able to do during our tutorial, some of the questions which we are not able to do, you take them as homework exercises. You try to discuss among yourselves and all that and try to do, okay. Because it is possible that among the tutorial, because typically we have 1 hour for tutorials, so we may not be able to, we may be able to do some questions, may not be able to do some questions. Other questions which we are not able to do, you please take them as homework exercises, okay. Okay, clear? Yes? Any questions? You have any questions from the lecture in the morning? Any questions? No. So tomorrow 9:30, please come here, because Professor Subba Reddy will take class 1 hour. Then 11 o'clock I will come. Okay.
request all the participants to sign the attendance list.